Hello, everybody. This is tutorial 5. Uh, we're building a model for electric voltage and how they relate to electric circuits. So let me share my tutorial page. Okay, and we should be seeing that. Hmm, there we go. Okay, now this turns out to be one of the easier tutorials that were ever produced, and that's good news because we're ready for an easy one. Um, and some of the first part of this tutorial is review, something that you've seen before. So let's just go through this first page fairly quickly. The circuits at right contain identical batteries, identical bulbs, and unknown identical elements labeled X. They're unknown to us, but they're the same as each other. How do the bulbs compare in brightness? Now, we've seen in the previous tutorial that turning the battery around just doesn't change anything. And so I can think of these two circuits as being the same with either the elements reversed or the battery reversed, either way. And the bulbs are going to be exactly the same brightness. In each circuit, how does the current through the bulb compare to the current through element X? Uh, Also the same. What goes around comes around. And that's just a kind of an offhand way of saying that current doesn't get used up as it goes around a loop. It's got to be preserved or conserved. Now we replace one of the box X's with a box Y, and we don't know what's in it, but we know it's different than X. And we're assuming that there's no batteries in either box, so that we just have passive elements like bulbs. It's observed that the bulb on the left is brighter than the bulb on the right. So I'm going to represent that with rays coming out, and these would have smaller rays. And that tells me that there's more current going through this battery on the left. And we found that when things are in series, the resistance of the circuit is um, the sum. And so that tells me that uh, since the resistance of this circuit on the right is greater, that tells me that the resistance of a bulb plus the resistance of Y has to be greater than the resistance of a bulb plus the resistance of X. And since I've got a bulb on both sides, I just ignore that. And I say that the resistance of Y is greater than the resistance of X. Now, in each circuit, does the current through the bulb, how does the current through the bulb compare to the current through the unknown element? Again, same. What goes around comes around. In each circuit, how does the current through the bulb compare to the current through the battery? It's the same. It's an indicator bulb. Okay. Well, that was quick. Well, now we want to predict the brightness of these three identical bulbs, B1, B2, and B3. And we have these elements that are in series with the three bulbs. And last day, uh, we found out something about the resistance of these uh, circuits that are in the boxes. And what we found was that two bulbs in parallel had the smallest resistance, And one bulb had larger resistance, but two bulbs in series had larger still. And so based on that, I would predict that two is going to be the brightest bulb and that one is going to be the second brightest bulb and that three is just going to be dim if we can see it light at all. And what does our prediction imply about the relative currents through the batteries? Well, that means that the current through the second battery is going to be greater than the current through the first battery and greater than the current through the third battery. And that's because B1, B2, and B3 are again indicators. There are I into the battery. They tell us what's flowing through the battery. Um, we we saw these circuits both in class and in last week's tutorial, so we're just gonna skip right over that. Um, Now we're going to get um, into the meat of this tutorial, and that's measuring potential difference. Now, you know, I told you about the promise I made to just avoid the word potential and change that for voltage. But this particular tutorial was published by Lillian McDermott and Peter Schaefer at University of Washington, um, not by me. And so uh, I didn't get to have a vote on what they were going to call that there, but I'm going to call it voltage whenever I can here. Uh, for the remaining circuits in this tutorial, we're going to use a battery holder with two batteries connected in series. The two battery connection or combination will be treated as a single circuit element. So what we've drawn here as a battery is indeed two batteries in in series, but we're just going to lump them together uh, as a single battery. Now we're going to start with a single bulb circuit. And what we want to do is measure the voltage across the battery in that circuit and the voltage of the bulb in that circuit. The first experiment we're going to do, I'm going to connect a single bulb to my battery pack. And you see that it's very bright, very bright. Now, if I measure the voltage across the battery by putting the leads in here, you see that we get, looks like it's around 2.89, 2.9. Okay. Now, if we measure across the bulb, what we get is 2.87. So pretty much the same. If we were to measure the voltage across these wires that are not perfect, we would find that there's a little bit of voltage across those, but perfect wires would give us absolutely no voltage across the wires. Okay. Okay. So what we found was that the voltage here was 2.9 and the voltage here was about the same, 2.83. Okay, how does the voltage difference across the bulb compare to the voltage difference across the battery? Well, they are about the same. Okay. Now we're asked to set up the circuit containing two bulbs in series as shown and rank from largest to smallest the current through bulb 1, bulb 2, and the bulb in the single bulb circuit from part A. Well, the single bulb circuit was the brightest, so it must have the most flow going through it. And we saw that bulb 1 and bulb 2 were equally dim. So this one was very bright, and these were equally dim. And so they would be equal as far as current is concerned. Now, let's measure the voltage difference across each element in the circuit. Let's look at the second experiment. Here we hook two bulbs that are in series with each other. And I'm not sure if you can see that well over the zoom, but these are much dimmer than the single bulb, but they look identical to each other. And if I bring my voltmeter up here and take the voltage reading across the battery pack, I get 2.93, which is similar to what we had before. If I measure the voltage across one bulb, I get 1.47. If I measure it across the other bulb, I get 1.42. Okay, what we found was 2.92 across the battery and 1.47 across bulb 1 and 1.42 across bulb 2. How does the voltage difference across the battery in this circuit compare to the voltage difference across the battery in the single bulb circuit? Well, it's almost the same. We briefly discussed in class that if these batteries rather were ideal, I would get exactly the same number. But sometimes when uh, a non-ideal battery is asked to deliver more current than it can keep up with, the voltage across the terminals changes slightly. Rank the voltage difference across bulb 1 and bulb 2 and the bulb in the single bulb circuit from part A. So the voltage across the single is twice as much as the voltage across bulb 1, which is approximately equal to the voltage across bulb 2. We're not going to concentrate on small differences. How does the voltage difference ranking compare to the brightness ranking of the bulbs? The same. The bulb that has the more volts across it is the brighter bulb. Predict what the voltmeter would read if it were connected to measure the voltage difference across the network of bulb 1 and bulb 2 together. So from here to here. Well, if I add those two voltages, 1.47 and 1.42, that's going to give me 2.89. 2.89. How does the voltage difference across the network of bulbs compare to the voltage difference across the battery? Well, the voltage across the battery, remember, was 2.92. And so almost most without that, almost the same. Okay, now let's set up the circuit with two bulbs in parallel as shown. Rank the current through bulbs 1 and bulb 2 and the current in the single bulb circuit from part A. Well, they're all equally bright, so the current through the single is equal to the current through bulb 1 is equal to the current through bulb 2. How does the current through bulb 1 compare to the current through the battery? Well, the current through bulb 1 is equal 1/2 the current through the battery. And I know that because the current through the battery comes to this junction, and half of it goes through 1 and half of it goes through 2. If we measure the voltage difference across each circuit element, well, let's do that right now. I have here a circuit that has two bulbs in parallel with each other. I see direct connections to both sides of the battery for each of the bulbs, and they're both equally bright and very bright as a single bulb. And now let's make some measurements here. If I measure across the battery, what I find is 2.8, fluctuates a little bit as they're around 2.82, 2.83, 2.82 in that neighborhood. Okay. And then if we take a measurement across this first bulb, the one that's closest to the battery, I get 2.85. And if I take the measurement across the second bulb, I get 2.85. Okay, let's take the measurement across the battery again. What I get there is 2.86, 2.86, 2.87. Okay, good. What we found um, is the voltage across the battery was 2.86. The voltage across bulb 1 was 2.85. And the voltage across bulb 2 was 2.85. How does the voltage difference across the battery in this circuit compare to the voltage difference across the battery in the single bulb circuit? Well, remember, um, in the single bulb circuit, it was 2.9. So again, almost the same. And I spelled it correctly this time. Rank the voltage difference across bulb 1, bulb 2, and the bulb in the single bulb circuit. Well, the bulb in the single bulb circuit was 2.83, so they're almost the same. How does the ranking by voltage difference compare to the ranking by brightness? Exactly the same. Answer the following questions based on the measurements you have made so far. Does the current through the battery depend on the circuit to which it is connected? Yes. As the resistance of the circuit goes up, the current through the battery goes down and vice versa. Does the voltage difference across the battery depend on the circuit to which it is connected? Not for an ideal battery. Our model for electric circuits includes the idea that for ideal bulbs, the brightness of a bulb is an indicator of the current through the bulb. Based on our observations in this tutorial, we can extend the model to include the idea that for circuits containing identical bulbs, the brightness of a bulb is also an indicator of the voltage difference across the bulb. Now notice that we always talk about the current through the bulb. The current is the flow of the charge through the wires, through the filament, through the bulb. But we always talk about the voltage difference across the bulb, from one side of the bulb to the other side of the bulb, because voltage doesn't flow, it doesn't go anywhere. It's like a pressure difference from one side of the bulb to the other side of the bulb, and that pressure difference is what pushes the current through the bulb. Set up the circuit with 3 bulbs as shown and observe their brightness. Okay, let's set that up. Before making the voltmeter measurements, predict the ranking of the potential voltage difference across the battery and each bulb. Explain your prediction. Well, we're just going to make the measurement. Okay, let's look at this one here. What I have is from one side of the battery through a single bulb, and then from that single bulb, we branch out to 2 bulbs in parallel with each other. And what we see is that the 2 bulbs in parallel with each other are dark. They look like they're out. But if I look really closely, I see that there's a tiny little uh, light. But we're tempted to say there's nothing going through these bulbs since they're dark. But we know that whatever's flowing through this first bulb has to split right here 50-50 through the 2 identical bulbs. So each of these bulbs have exactly half what's going through the bright bulb. And so we see that the relationship between flow and glow is not a linear one. Indeed, if I were to take a second battery and see one more wire here and put 2 battery packs in here, what I get is I see those dim bulbs are lit now, and the single bulb is super, super bright. It may pop at any moment here. So let me go back to just 1 battery pack so that we can make our measurements. And so if I take the voltmeter that you can see and take the reading across the battery, what I get is 2.88. 2.88. And then I'm going to take the reading across this bright bulb, and I get 2.48. And now if I take the reading across this dim bulb, I get 0.4. And if I take a reading again across the dim bulb that is parallel to the other dim bulb, I get 0.40. Okay, well, that worked out very nice. We found in that case that the battery was 2.88, that bulb one, which is this single bulb here, and it was bright, and these guys were so dim that we couldn't see a glow, but we knew that they had to have half the current that was going through the bright bulb. The bright bulb had a voltage of 2.48, and each of the dark bulbs had a voltage of 0.40. Okay. Before setting up the circuit shown at right, predict the ranking of the currents through the battery and each bulb and explain. Well, the current through the battery is going to be the biggest because all the current flows through the battery. And then when it gets to this point here, it splits with more than half going the easy branch and less than half going the hard branch. So I would say the next one would be the current through branch with bulb one, and then that would be greater than the current through bulb two, which has to equal the current through bulb three. Predict the voltmeter measurements across each element in the circuit there. Well, I would predict that if the battery stayed to be 0.288, then the voltage across bulb one should be 2.88, and the voltage across bulb two, if these are truly identical bulbs, would be half of that, or 1.44 and 1.44. Let's set up the circuit and check our predictions. Let's do this one where I have okay. In this experiment, we have one branch that has a single bulb on it and a second branch that has two bulbs in series. And if we look at the voltage across the battery, we get 2.84. The voltage across the single bulb, 2.82. The voltage across one of the series bulbs, 1.42. And the other one is 1.37. Okay, we're back here. Let's check our predictions here. The battery voltage was a little bit less, 2.84. And again, that's because we're pulling more current through that battery than we were up in this exercise up here. and that's going to cause the non-ideal battery to have a little bit of trouble with that. But we found with the single bulb branch, we had 2.82, which is almost the same. And for the others, we had 1.42 and 1.37. And okay, so these are not quite the same. And again, our wires are not perfect. Our connections where they are clipped to the little holders were not perfect. And so we get a little bit of a voltage difference across those resistances there. Both circuits at right have more than one path for the current. Sketch all possible current loops on the diagram. A current loop is a single path of conductors that connects one side of the battery to the other. Okay, let's do that. I've got this one that I'm going to call loop 1. And I have this one that I am going to call loop 2. And I have this one that I am going to call loop 3. And I have this one that I am going to call loop 4. For each of the current loops that you have drawn, calculate the sum of the voltage difference across the bulbs in that loop. Okay, so if I go here, for loop 1, I have 2.48 plus 0.40 is equal to 2.88. For loop 2, I have the same thing, 2.48 plus 0.40 is equal to 2.88. For loop 3, we have well, there's only one bulb there, and it's 2.82. For path 4, we have 1.42 plus 1.37, and that's going to equal 2.79. How do the sums of the voltage differences across the bulbs in each loop compare to the voltage difference across the battery? For these two, it was exactly the same. And here it was almost the same. Okay, we don't need to check with the tutorial instructor because that are me. Okay, that's the published tutorial. We'll discuss that in class. Okay, we set up these 5 circuits a while ago with small flashlight bulbs and small batteries, and we found that the batteries sometimes had trouble keeping up with the current that we were asking for. So we're going to do them again with this car battery and see if things go better. I'm going to make each of these circuits in turn, and then we'll measure the voltage across the battery and the voltage across each of the bulbs. So let's start with this single bulb circuit, and I'm just going to plug in there and there. Now, I'm going to start by measuring the voltage across the battery, and I've got it set on ohms because I was measuring the resistance of the bulb. Let's put it on voltage, and we get 12.57. So I'm going to write that up here. And I'm going to leave off the volts there just to save us some time. And now I'm going to measure the voltage across the bulb. 12.41. Okay. Okay. Now we're going to put that aside and bring these guys over close. And now we've got two bulbs in series, and we will start with the battery again. 12.56. Okay, about the same as what we had before. And now we'll measure across the bulbs. I've got 6.28 and 6.15. Now, if those bulbs were truly identical, if they had really been made at the same factory by the same worker on the same day, I would get the exact same number there for those. Now, if I add those numbers up, what we get is 12.43. So very close to the battery voltage. Okay, now we're going to move these to the side. Oops, sorry. Stay. Bring these down. And my battery. These are two bulbs in parallel with each other, and see how bright they are. They're just as bright as our single bulb, and we can see that by disconnecting one of them and seeing that the other one doesn't change. And so we're going to go back and measure the voltage across the battery. Now, what do we expect? We're drawing more current, twice as much current as we did with the single bulb. And so we expect the battery to have a little bit of trouble keeping up with that, and it's going to drop its voltage a little bit from that of a single bulb. And 12.35, that's what we see. Again, if it were an ideal battery, there wouldn't be any drop at all whatsoever. Now, as I measure across the bulbs, I get 12.14 and 12.08. Okay. Now, here's a fun little exercise. If I no, that's going to take too much time. I was going to say, if I were to make these wires better, less resistant, more perfect, I would get exactly the same number on this one as that one. But we've got a little bit of resistance in these wires here. Okay, the next one that we're going to try and do will be this one here. I'm going to need the single bulb, oops, up here, and I'm going to take that and that and now we, okay, almost ready. Plug the positive terminal is plugged into this bulb up here, and then it branches down to these two bulbs in parallel, and then that's going to be connected to the negative terminal of the battery. Now, just as we saw with the smaller bulbs, this one's very bright, but these guys are dark. I mean, I can't see hardly any glow at all. And yet I know from what we know about circuits that half of the current through this bulb has to go through that bulb, and half has to go through that bulb to get back to the battery. So we see that twice as much current is not twice as bright. We also find that there's a much bigger voltage across this bright bulb than across these dim bulbs. Now, let's go back to the battery first. The battery here, 12.51. Does that make sense? Well, let's put it in here. 12.51. Okay, we're drawing more current than this one here, and so I would expect it to be lower than this one here, and that's what we see. Okay, now let's measure the voltage across this top bulb. What I see is 10.31. And now we'll do it across each of these bulbs here. 2.08 and 2.075. So 2.08 either way. Okay, now if we add up any path here, I've got 10.31 and 2.08. That's going to be 12.39. Again, very close to our battery voltage. So one last circuit. We are going to make this circuit with our single bulb. Let's get rid of these guys and bring in these guys. And I'm gonna need that and that. Okay, you see that this would be that bulb there, and these guys are those bulbs there. So let's hook up our battery. Now we've got a little bit more resistance than this one here, so we should get a little bit more voltage there, less current. Okay, so let's measure the voltage across the battery. oops, had a 50-50 chance. 12.41. Okay, and now we're going to measure across the single bulb. We get 12.21. And now we measure across the two bulbs in series, and we get 5.88, 5.89, and 5.9. Very nice. So essentially 5.9, 5.9. Okay, so that is, so if we add that up, we've got 11.8 volts there. So that surprises me a little bit that that's so much less. 5.95 and 6.02. Okay, I didn't have a good connection there before. So I've got 5.95 and 6.02, and that's going to add up to 11.97. Okay, so we're seeing a little bit of resistance in the wires, but what we see is that parallel branches should have about the same volts across them, and we'll understand why that is in Tuesday's lecture when we discuss our voltage model for circuits. So I hope this has been helpful and has clarified the tutorial. Let's end there.